questions about Newton's second law, part 3, percent error. So in the lab that we did for this, we needed to consider the fact that we had a cart with a massless string and a hanger, and we kept adding bars to the cart, which increased the mass of the system, but we did not change the mass of the hanger, which kept the net force was constant, right? It was our constant variable. So when we did this, masses got bigger and bigger, the acceleration got smaller and smaller, and we had an inversely proportional relationship with the acceleration and mass of the system. To linearize this graph, we made an acceleration versus 1 over the mass of the system graph, which had units of 1 over kilograms, that helped linearize the data, which looked like this. For the sample I'm going to do today, we're going to pretend that my slope was 0.333 meters per second squared per 1 over kilograms, which we showed unit analysis in class later that this could be rewritten as 0.333 newtons, because a meter per second squared divided by 1 over kilograms ends up being meters per second squared times kilograms, which is newtons. So this is what we're going to use for the sample slope today. Well, in addition to knowing your slope, which we could put this down 0.3333 newtons, or you could have written meters per second squared per 1 over kilograms. We also need to know what the scientifically expected value for the slope is. In other words, what was the slope supposed to have been? Well, when changing the mass of the system and measuring the acceleration, what did we not change? The net force. And after analysis in class, we figured out that the physical significance of the slope is the net force. So how would we calculate the actual net force? How would scientists say what was the net force on the system, or what's causing the system to accelerate? Well, just as in all versions of the lab, the thing that caused this to accelerate was the weight of the hanger, right? Gravity pulling on the hanger made our system accelerate. So to do that, we had to calculate the weight of the hanger. To do that, you do G sub E times the mass of the hanger. And you'd have to fill in your own mass of the hanger. For the sample I'm doing today, we're going to assume that we use 9.81 newtons per kilogram because it is a lab. And we're going to use a 35-gram hanger, which had a mass of 0.035 kilograms. And I think you guys all used a 50-gram hanger, so you'll have to put in a different value in there for that. And when you do 9.81 newtons per kilogram times that, you get I think it's 335 newtons. So, and I believe you already calculated net force on the top line of your part 3 data sheet. So these are the two values we're going to need. The actual slope that you had, which I have in red here, and then the scientifically expected value in the blue box. Let's take a look. So for all percent errors, you have to do the scientifically expected value minus your slope, and it's the absolute value of that difference divided by the scientifically expected value, and you multiply it by 100. Just as we talked from the other sheet, in this experiment, the net force, or the scientifically expected value, is the net force, and you're comparing that to the actual slope you got, and you'd be dividing by the actual net force, the scientifically expected value, times 100. So now we fill in those values. The actual net force was 0.34335 newtons. We subtract from that the slope, 0.333, and you could put newtons or meters per second squared per 1 over kilograms. That all turns out to be newtons. Take the absolute value of that difference and divide by 3.335 newtons, multiply by 100. And when you punch all that in, you end up with about a 3% error. If I remember correctly, most of the groups this year had slopes in the 0.45 to 0.49 range. And again, your scientifically expected value for your slope should be listed as whatever the net force is on line 1 of your part 3 data sheet. I hope that helps.